The chain rule is the rule for differentiation that allows us to differentiate composite functions, or functions that are compositions of other functions. So our first task, and that what we'll look at in example 1, is just recognizing when we have a composition, and sometimes it's easy for a composition to look like a product, so especially important to be able to distinguish between those two. So remember, a composition is when one function is the input for another function, and the notation we usually use is f circled g of x, or f of g of x, but when one function is nested inside of another function. So if you take a look at the 4 functions here in example 1, one of them is definitely not a composition, and that would be the first one. In the first function, we just have a product of 2x times cosine x. So when I read that, I'm not reading anywhere a function of another function, but rather just multiplication. So 2x times cosine x. So this is not a composition. The next one, f of x equals cosine of 3x plus 2. Here, the input for cosine is not just x, it's another function, 3x plus 2. So this is a composition. And it's going to help us to be able to recognize the inside function. And that function, oftentimes we're going to use the notation u. So we could think this is cosine of u, where u is 3x plus 2. So I think of this 3x plus 2 as the inside function, and the cosine function as the outside function. And again, example 3 is also a composition because I have square root of not just x, but square root of 3x plus 2. So we could think of this as the square root of u, where u is 3x plus 2. And we would think of this as the inside function of the composition, and the square root function as the outside function. Example 4, we could think of this as just a product, sine of x times sine of x, but we can also think of it as a composition, and sometimes it helps to rewrite, even though the convention is to write the exponent on the trig functions right next to the function itself. When we're working on these derivatives, it helps us to remember that it's actually the square function that's on the outside here, if we rewrite it in this form. So rewrite it as sine of x in parentheses, that whole group, squared. So we could think of this as u squared, where u is sine of x. And so the inside is the sine of x function, and the outside would be u squared, or just the squaring function. So once we've established that we have a composition and we can recognize what is the inside of this composition, what is the outside of this composition, then we can start to take the derivative for this function. And we're going to write the notation a couple of different ways. One says the derivative of f of g of x is f prime of g of x times g prime of x. And it almost helps, I think, to have that in words. So it says take the derivative of the outside function with the inside function as its input, and then multiply the result that you get from that by the derivative of the inside function. And the reason I've been introducing u in those first 4 that we did was that the Leibniz notation for this process is actually helpful, especially as we're just getting started. The Leibniz notation would say dy dx is dy du, or the derivative of y with respect to u, times the derivative of u with respect to x. We'll use this notation just to get started, and then we'll talk about how it is exactly the same as what the part here is saying and what this sentence is saying. But once we have more than 2 layers, this Leibniz notation is going to get a little bit complicated. So we want to have we can use it just to kind of get started, but then we'll work our way away from it so that we can more quickly get through derivatives of functions that have maybe 3 layers or 4, or also involve a product or something like that. But in example 2, we will differentiate the 3 from the first example where we saw that we had compositions. So what I want to do is rewrite this as y equals sine of u, where u is x squared plus 3x. And like I said, at first I want to go ahead and use this Leibniz notation. And it says dy dx should be dy du times du dx. Okay. So rewriting our function as y and then rewriting the inside as u, I can say, well, if y is sine of u, dy du will just be cosine of u. And if u is x squared plus 3x, then du dx will just be 2x plus 3. And we're almost done, except we still have this u here, and I don't want u's, I want just everything in terms of x's. So then the last step would be to replace that input for cosine. So I'll say, okay, what I actually want is cosine of u, but u was x squared plus 3x. And then times the derivative of u with respect to x, which was 2x plus 3. Right, so notice I have the derivative of the outside, which was sine, evaluated at the inside function, so with its input just left alone, right? I do the derivative of the outside, I differentiate sine, I get cosine, but I leave its input the same, and then I multiply by the derivative of the input, which would be the derivative of x squared plus 3, and that's where this 2x plus 3 came from. So I have 2 pieces here. The derivative of the outside evaluated at the inside, multiplied with the derivative of the inside. So let's do the same thing on the next one. I'm going to rename my function as just y, and I'm going to rewrite sine of x squared as u squared and make a note that u is sine of x. And then I'm going to use the Leibniz notation, which says dy dx is the same as dy du times du dx. Right, the derivative of y with respect to u times the derivative of u with respect to x. And so when I put the pieces for dy dx together, I will have dy du would be 2u, and du dx, the derivative of u with respect to x, that would be cosine of x. So I want 2u times cosine of x. And then again, just like last time, I don't want to leave this u here, so I will replace u with sine of x. And I can see then this is the derivative of the inside evaluated at the outside. The derivative of the outside evaluated at the inside. So leaving the inside the same times the derivative of the inside. All right, so let's do one more using that Leibniz notation. So I would rewrite this as y equals cube root of u with u equals x squared plus 1. Right, and I'm trying to get to dy dx. And so I will do dy du times du dx. And so we'll say dy dx is going to be, first I'm going to rewrite the cube root of u as u to the 1/3. So I'll have 1/3 u to the -2/3 when I use the power rule there. And the derivative of u with respect to x should just be 2x. So times 2x. And then again, I need to replace u. So I will do 1/3, put u back in, x squared plus 1, and to the -2/3, and then times 2x. That would be just fine, just for the practice, since I know sometimes students struggle with getting back and forth between especially negative and rational exponents, and a nicer form. Let's work on that. So let's see, the 2x will stay in the numerator, 3 is in the denominator, and the x squared plus 1 group is going to move to the denominator with an exponent of +2/3. The 3 in the denominator of the exponent means I'll have a cube root, and then I would have x squared plus 1 with an exponent 2. So that's how I would rewrite 1/3 x squared plus 1 to the -2/3 times 2x if I wanted a nicer form for it. So here's what we're thinking again. I want to keep in mind, I want the derivative of the outside evaluated at the inside times the derivative of the inside. All right. So in example 3, we're asked to differentiate, and now we might have either several layers to our compositions or some compositions involved in products or quotients. So you can see in example 3a, I have x squared plus 1 times the square root of x squared plus 2. Right? So I've got a product, and I have a composition as one of the factors. But only the second factor is a composition. So I need to think, well, I have the product rule going on, but I also, in the middle of that, will have a chain rule when I differentiate the square root of x squared plus 2. So we can look at the square root of x squared plus 2 as the square root of u, where u is x squared plus 2. And if we want to, we could do some side work here and say the derivative for just that part will be the derivative of the outside function evaluated at the inside function times the derivative of the inside function with respect to x. And so dy du would be the derivative of square root of u, so 1/2 u to the -1/2. And the derivative of u with respect to x would be 2x. I would put u back in, and u was x squared plus 2. And then I could simplify that. So that's just some side work as we're getting used to this process, just doing the derivative of that square root of x squared plus 2. So if we go back to the big picture here, dy dx for the whole thing, I'm going to have the first factor times the derivative of the second factor. So I'm going to map this out using this d dx notation. Remember, d dx in front of something means the derivative of that thing. If you're not wanting to take the derivative yet, just map out your plan. This is helpful notation. So I'm saying I want the first factor times the derivative of the second plus the second factor, just left as it is, times the derivative of the first. So that's our strategy. I want to use the product rule. And then we already over here on the side figured out what the derivative of square root of x squared plus 2 is. So we'll have x squared plus 1 times, looks like x over square root of x squared plus 2. If I take this negative 1/2 exponent, put x squared plus 2 in the denominator with a positive 1/2 exponent, that's what I would get. And then plus square root of x squared plus 2 times the derivative of x squared plus 1, so times 2x. Right, so I have all my derivative factors in green and the other factors there in blue. In 3b, we have the first example of a 3-layer composition. So again, when you have the power of a trig function like that right next to the trig function, it's helpful to rewrite it just so you can think of it more clearly with the exponent on the outside. So we have sine of 3x plus 5, and then that whole group to the third. So here, like outside, I have the cubing function. So we could call it u cubed if we want, but this time that inner function u is actually 2 layers itself. So let's say the middle function would be the sine function. I'll maybe say sine of v. And then the inside would be 3x plus 5. And that would be like what we might call v because we had sine of v there. So outside is the cubing function, middle is the sine function, then inside is the 3x plus 5. When we have 3 layers like that, and just a composition, not a product or a quotient or anything else, we're going to have 3 factors because we're going to have 1 factor for each time we take a derivative of one of these 3 functions. So let's just talk our way through it. And I'm not going to try to use the Leibniz notation. I'm just going to think, I want the derivative of the outside, which was a cubing function. So I know I'm going to have this shell of 3 times something squared. And what I want to put inside is everything that was inside the cubing function. So the cubing function had inside of it sine of 3x plus 5. Right, so I change nothing about the inside. I only take the derivative of the outside, so 3 and then the exponent 2, and then I leave the input just the same as it was. Then I move on to the middle, which was sine of 3x plus 5. And so what I want to do is now take the derivative of sine, which was the outside function there. The derivative of sine is cosine, but I don't want to change the input. So the input needs to stay exactly the same. The inside or the input of sine was 3x plus 5. So that stays the same. And then the last thing I do is take the derivative of the inside. The input for cosine, or the inner layer of this whole function, was 3x plus 5. So now I'm doing the derivative of 3x plus 5, and that's just 3. So you can see I have 1, 2, 3 factors, 1 for each of the layers of the composition. example C is similar, but now I have 4 layers because I have the power of 33, I have a sine function, I have a cosine function, and then the innermost function is a quadratic function. So we see when we do the derivative, dy dx will be, first I'll take the 33rd power and differentiate that function. So I'll have 33, leave its input the same, and then to the 32nd power. Right, and the input for the 33rd power was sine of cosine of x squared plus 4x plus 5. So that stays exactly the same. And now I look at the layer that's right inside the 33rd power, and that would be the sine function. I differentiate the sine function and I say, okay, the derivative for sine is cosine, but I'm not changing the input for the sine function, which had been cosine of x squared plus 4x plus 5. The next layer, after I've differentiated sine, excuse me, I need to differentiate cosine. The derivative for cosine is negative sine, and I need to leave its input the same. The input on cosine was x squared plus 4x plus 5. So that will be the derivative of cosine of x squared plus 4x plus 5, except that I need one more factor, which is the derivative of this innermost layer. So times 2x plus 4. Right, and that was our innermost layer, so now I don't need to do any more multiplication. I don't need to do the derivative of 2x plus 4, because 2x plus 4 was not one of the original functions. It's the derivative of the innermost function. So once you've written down the derivative of that inside function, you stop. And again, you can see I have 1, 2, 3, 4 factor groups, and I had 4 layers to this composition. Okay, so example 4 says differentiate this function. Now I have sine of 5x squared plus 2x, and that whole group to the 3rd power. So as I've been recommending, let's rewrite what happened here. Let's get rid of this triangle for one thing. Let's rewrite sine, instead of having sine with the exponent 2, let's write sine of 5x squared plus 2x, and then that whole thing to the 3rd. So notice that our very outside function here is the 3rd power. And inside of that I have a sum, and one of the terms in the sum is a composition with, it looks like 3 layers. But the very first thing I need to do is deal with that power of 3. So I'll take 3 and I'll leave a place for its input, and I'll make the exponent 2. So that's the derivative for the 3rd power. And I'll leave its input the same. So I'll leave that exponent as a 2, not change it to a 3. Leave the input for the cubed function the same. And then I need to multiply by the derivative of the inside. So I'm just going to write that down, derivative of the inside. So let's go now through the process of doing the derivative of the inside. We'll have 3, and then this stays the same. And now we want the derivative of the inside, and the first term on the inside is a composition. The outermost layer of that composition is the power of 2. So I want 2 and leave the input the same. And then I right away next to that need to multiply by the derivative of the inside, which would start with a cosine, because that's the derivative of sine. Leave its input the same. So cosine of 5x. And then lastly, multiply by the derivative of 5x, which would just be 5. So these factors that I just wrote down are the derivative of sine of 5x squared. And then right next to that, I want to then add on the derivative of 2x, which will just be 2. So you want to make sure that that plus 2 is separate from all those other factors. You don't want to add 2 and then start multiplying by the derivatives of the insides and things like that. And that should take care of it. So all of this here that we just wrote down between those brackets will be the derivative of sine of 5x squared plus 2x. All right, then in example 5, we're asked to find the derivative of, the second derivative of f of x equals secant of pi x squared. So again, let's rewrite this as secant of pi x squared. And the first derivative will only involve the chain rule. We don't have any products or anything like that. So chain rule will first deal with the power of 2. So we'll move the 2 down, new exponent would be 1, and leave the input the same, secant of pi x, and then multiply by the derivative of the next layer, which is secant. So derivative of secant of u is secant of u times tangent of u. So here we want secant of pi x times tangent of pi x, and then we want that times the derivative of the innermost layer, which was pi x. So we want one factor of pi. Sometimes students want to put 2 factors of pi out here, but it's just the derivative of the inside of the original function. So I don't need a factor of pi from each of these. These were just the derivative of secant. What I need is just the derivative, for my last factor, just the derivative of the inside layer of the original, which was just pi x. So just one extra factor of pi. So here's the first derivative of our function, and let's clean this up a little bit just to make it easier to take the second derivative. It looks like I have a factor of 2 and a factor of pi, so I'm going to put those out front. And then I have 2 factors of secant of pi x. So I'm going to write that as secant of pi x squared. And then I have a factor of tangent of pi x. Okay, so now we've got this rewritten. So now when I want the second derivative, I can see, well, I have this constant multiple 2 pi, so I'm going to do that. I'm just going to write that down, times the derivative of these 2 factors. So I'm going to need the product rule. And I'm going to just map out my plan here. So I want to leave the first factor just like it is, and then multiply by the derivative of the second factor. So again, I'm not going to take that derivative, I'm just going to write my plan down for now. Plus the second factor times the derivative of the first factor. all of that is multiplied by 2 pi, so I do need one closing parenthesis there. Okay, so I've just mapped out my plan. I'm carrying this 2 pi along, since that's a constant multiple. And now I have secant of pi x squared and times the derivative of tangent of pi x. There I have a composition, so first I'll differentiate tangent, which is secant squared. So that will be secant of pi x squared times the derivative of the inside layer, which would be pi. So here, these are the derivative of tangent of pi x. Then right next to that, I'll have plus tangent of pi x times the derivative of secant of pi x squared. And we already have that. That's exactly what we had for the first derivative, right? So when we differentiated secant of pi x squared, we already have done that work. I don't want to do that work again. So I'm going to just rewrite what I had from f prime. So derivative of secant of pi x squared was 2 pi times secant of pi x squared times tangent of pi x after we simplified it. Right, so I'm just taking what I had from f prime, which was exactly the derivative of secant of pi x squared, and I rewrote it here because that was the same thing as f prime. So I was just using some of the work we had already done to get through that second derivative a little more quickly, at least just that last piece. All right, in example 6, we'll get back to a derivative that's not quite as complicated, but just getting it cleaned up and being able to work with it will be a little bit more of our difficult task in this one. So here we're asked to determine the points at which this graph has a horizontal tangent line. So you want to remember that horizontal tangent line means the derivative is 0 because the slope of the tangent line is 0 if the line is horizontal. So we want to find the derivative and set it equal to 0, solve for x. And then we'll find the y coordinates. Those are always our steps for this kind of problem. So let's take a look at this function. So it says f of x is x over square root of 2x minus 1. I'm just going to rewrite that denominator as 2x minus 1 to the 1/2. And if I'm going to do the derivative, I could rewrite it as a product, or I can just leave it in this form and do a quotient rule. I think that's what we'll do. So quotient rule, I need low d high minus high d low divided by low squared. So low would be 2x minus 1 to the 1/2. D high is just 1 minus high. D low is going to get a little bit complicated here because we have a composition. I don't have just square root of x, I have square root of a function of x. So I will do, for d low, I want to first differentiate the half power. So 1/2, leave the inside part, the 2x minus 1, exactly the same. Change the exponent to negative 1/2, and then multiply by the derivative of the inside, which is just 2. So right here, I needed the chain rule. When I was doing the derivative of the denominator. And then I need to divide by low squared. When I square that denominator, I'll just have 2x minus 1. So let's clean this up. F prime of x. This would look like square root of 2x minus 1 in the numerator minus, let's see, these 2's will cancel. So x over square root of 2x minus 1, also in the numerator. And then in the denominator, I have 2x minus 1. So I want to figure out a way to clean this up a little bit. I like to clean up my complex fractions by multiplying by the LCD of the denominators of everything involved. And the denominators here are 1 and square root of 2x minus 1 and 1. So I'm going to multiply in the numerator and the denominator by square root of 2x minus 1. And then I haven't changed anything, I've just changed the look. So I'll distribute up here. And I can see now when I distribute the square root of 2x minus 1 to the first term in my numerator, that's just going to give me 2x minus 1. And when I distribute to the second term in the numerator, the square root of 2x minus 1 in the numerator will cancel with the square root of 2x minus 1 in the denominator, and that will just leave me x. So I have minus x. And then in the denominator, I have 2x minus 1 times the square root of 2x minus 1. So I could rewrite that as 2x minus 1 to the 3/2, because this is to the power of 1, and then square root is the same as to the power of 1/2. When I multiply those together, I would add the exponents, and so I would get to here. So this will simplify to f prime of x equals, looks like x minus 1 over 2x minus 1 to the 3/2. So now that I have this fraction, I can say the derivative will be 0 if and only if x minus 1 over 2x minus 1 to the 3/2 is 0. But it's helpful to remember that a fraction is 0 if the numerator is 0 and the denominator is not. So really, here, all I really need to be thinking about, if I want to know where this is 0, I'm just worried about the numerator being 0. So this will be if and only if x is 1. Right, so I'm not worried about the fact that that denominator looks a little complicated. I just want to know where this is 0. So a fraction is 0 if the numerator is 0, and as long as the denominator is not also 0. And if x is 1, the denominator is certainly not 0. So here's the x-coordinate where we have a horizontal tangent line. And so the point at the horizontal tangent line will be 1 f of 1. So let's see what f of 1 is. That's 1, and then 1 over square root of 2 minus 1. So it looks like 1, 1. So you could take a look at that graph on a graphing calculator, and you should see what looks like a horizontal tangent line at the point 1, 1. In example 7, we're going to use a table of values of function values for two different functions, f and g, as well as values for the derivatives, without being given a formula for either f or g. And then we're going to use those to evaluate derivatives of functions that are combinations of these two unknown functions. So in example A, we have h of x equals f of g of x, and we want to find the derivative of h at a equals 0. So if we think about the structure, we can see h is a composition of two functions, so we need the chain rule. So when I do the derivative for h, I want to do the derivative for the outside function, which would be f, evaluated at the inside function, so leave the inside function as its input, and then multiply by the derivative for the inside function. So that's the general pattern for h prime, and we want h prime at 0. So that will be f prime, or the derivative of f, evaluated at g of 0 times g prime of 0. One of these we can get directly from the table, one of the derivatives, that's g prime. I can see that g prime of 0 is 2. And then the other factor here, f prime of g of 0, I need to start with the inside. So I'll start with g of 0, and I'll find that from the table. When x is 0, I can see the function value for g is also 0. So I'll fill in 0 for g of 0. That means I want f prime at 0 times 2. So then f prime at 0 looks like that should be 5. So it appears that we should have 5 times 2, so 10 for the derivative of h, which is the composition of f and g at 0. In part b, now our function h is the quantity 1 plus g of x, and then that to the third. And now we want this evaluated at a equals 2. So again, let's write down the general pattern for how we would differentiate h. Again, I have a composition. The outside function is the cubing function, and then the inside function is 1 plus g. So I will take the derivative of the cubing function and leave its input the same. So I moved the 3 down and made the exponent 2, and I did not change the input to the cubing function. So there's the derivative of the outside evaluated at the inside. And then I need to multiply by the derivative of the inside. The derivative of 1 is just 0, and then the derivative for g I would write as g prime of x. So here's how we want to evaluate the derivative for h. And now we want h prime at 2. So I'll have 3 times 1 plus g of 2 squared times g prime at 2. So again, from the table, I'll get g prime of 2, and I will also find g of 2. Looks like g prime of 2 is -1, and g of 2 is 1. So if I fill those in, I have 3 times 1 plus 1 squared times -1. So that will be 3 times 2 squared times -1. So that should be, looks like -12. So again, we don't have formulas for f of x or g of x, but we know some values for those functions and for their derivatives at given points. And then we can use those table values to just evaluate derivatives for h, where h is a combination of the functions f and g. All right, example 8, we have the daily temperature in degrees Fahrenheit of Phoenix in the summer can be modeled by this function, where x is hours after midnight, and like it said, T is temperature in degrees Fahrenheit. And we're looking for the rate at which the temperature is changing at 4 p.m. So if we're looking for a rate of change of temperature, that's T prime. And at 4 p.m., let's see, midnight is 12 a.m. So we want to go to noon, that would be 12 hours later, and then 4 hours after that. So we would say, 4 p.m. would give us x equals 16 hours after midnight. So we want to find t prime of 16. That's our goal. So let's find t prime of x first, and then we'll fill in x equals 16. So as we're differentiating t, we'll say first the derivative of 94, that's 0. And then we have a constant multiple of 10. So we'll have 0 minus 10 times the derivative of cosine of pi over 12 times x minus 2. So here we have a composition. And cosine is the outside function, and pi over 12 times x minus 2 is the inside function. So we do the derivative of the outside function, which is negative sine, and then we leave the inside function the same. So we have negative sine of pi over 12 x minus 2 times the derivative of the inside function, which would be pi over 12, because that's a linear function, and the derivative for a linear function is just its slope. So times pi over 12, and that should be our last factor. So if we simplify this here, we have t prime at x is, let's see, I'm going to multiply the negative 10 with a factor of negative 1 on sine and just make this positive 10 sine of pi over 12 times x minus 2 times pi over 12. So I'm going to put that extra factor of pi over 12 in front with the 10. And then I might as well reduce that to 5 pi over 6 sine pi over 12 times x minus 2. So there's a nice form of t prime, and now we want the derivative at 16. So we'll have 5 pi over 6 times sine of pi over 12 times 16 minus 2, so that would be times 14. So that's 5 pi over 6 times sine of 7 pi over 6. That's actually one we can find without our calculator. 7 pi over 6, that's over here in quadrant 3. And the sine value there, the x-coordinate of that point on the unit circle, would be negative square root of 3 over 2, and the y-coordinate is negative a half. So the sine value there is negative a half. So I'll have 5 pi over 6 times negative a half. That would be negative 5 pi over 12. And we would say this is degrees Fahrenheit per hour. So it looks like the temperature is dropping at a rate of 5 pi over 12 degrees Fahrenheit per hour at 4 p.m. So let's find out what 5 pi over 12 is, just to see if this estimate seems reasonable. So I would say grab a calculator. And if I do 5 pi over 12, that's about 1.3. So it's not changing fast, but dropping a little bit at 4 p.m., that seems definitely reasonable. So we'd say the temperature is dropping at a rate of approximately 1.3 degrees Fahrenheit per hour at 4 p.m. All right, So we will certainly get more practice with differentiating compositions as we're going on to remaining sections in this chapter and really throughout the course. But hopefully you're starting to see how this chain rule works.